Hey, hello, Physics 123 students. As you know, we wrapped up our lecture today on chapter 21, and we've got one more chapter to do. And I said I would make a few examples that I would have liked to have done in class, didn't have time. So if you have some time, go through these. There's a few little techniques that are kind of nice to see and or dive into the problem so you kind of complete the homework here. Let me start with number 4. I got a list of, looks like 5 of them, and I'll grab the hard copy of the textbook here and drop it into the screen here. But it says, in the period of 1 second, 5 times 10 to the 23rd nitrogen molecules strike the wall that is an area of 8 centimeters squared. Assume the molecules move with a speed of 300 meters per second and strike the wall head-on in an elastic collision. What is the pressure exerted on the wall? And the mass of one nitrogen molecule is given here. Now, this one I thought I would do first because we kind of quickly looked at the book's derivation and didn't really do it ourselves. That kind of gave creed to the kinetic theory. And so if I imagine a box filled with a bunch of BBs, if you will, bouncing around, I'll just draw 4 of them here. 1, 2, 3, 4. They're going to hit and bounce off. Now in this say they're talking about a head-on collision. And so it's much easier in the sense that maybe if I looked at one atom, or molecule, I should say, it would come in with a speed of 300 meters per second, hit the wall, bounce off, and return with a speed of 300 meters per second. So if I look at the change of momentum of that one molecule, it would be mv final minus mv initial. And in this case, they give us the mass. In fact, maybe I will factor out the m here and say, all right, the change in momentum is this mass, 4.68 times 10 to the negative 26 kilograms, times, and then the final speed, I guess, is going to be a negative 300 minus the initial speed, which is 300. That together is a negative 600. So grabbing a calculator here, I would say that the change in momentum of 4.68 times 10 to the negative 26 multiplied by, and I'll go ahead and put the negative 600 so I can keep the negative, but it's negative 2.81 times 10 to the negative 23. And the unit for momentum, if you remember from last semester or 2 semesters ago, depending on when you took Physics 121, this would be the change in momentum of that one. Okay. Now, if we look at then the force on that one, which is change in momentum over time taken, and again, I guess I'm just looking at one of them, and so it says a period in 1 second, there's this many. So let's just say this one hits it and it doesn't hit it again during that 1 second. I guess you might say there'd be a massive force during the collision and then nothing for a while. So maybe you had to put an average here so we can put average time and average change in momentum. So this is minus 2.81 times 10 to the minus 23 kilogram meters per second. And the time is in 1 second, resulting in a force on average. Because like I said, when it makes impact, it's actually an enormous force, or enormous compared to what I'm just going to calculate. And then most of the other time, it's 0. And so actually, if there was only one molecule in the box, we probably wouldn't want to average it. We would just want to say, okay, there's no force, no force. Bam, it hits it. Oh, there is a force. No force, no force. Bam, it hits it. And then there's a force. And so it would be very step function-ish, okay? But if there's a bunch in the box, there's a certain percentage hitting it every, moment here. Anyways, this is that average force. And then notice the units come out to be newtons. So if I wanted to know the total force, I would multiply by the total number of molecules, which we use capital N. And I just wanted to point out, be careful, this is the N for newtons, and this is N for the number of molecules. So the number of molecules was given as 5 times 10 to the it's a lot, 23. Which is great because that 10 to the minus 23 and that 10 to the plus 23 are going to be canceling out. And so 5 times 1 is a 5, 5 times 8 is a 40, carry a 4, 5 times 2 is 10, and 14. So that would be 1405 newtons, or I'll just go 14 points. Should I round up? Sure, why not? 14.1 newtons. And then finally, to get the pressure, and I guess technically it's negative, but let me just say the pressure, then the absolute value would be the amount of force divided by the area. So this is 14.1 newtons, and they said this area was 8, and they said it was in square centimeters. So I'm going to do the standard square centimeters, but keep in mind that means that not only is the meter squared, like this, but the centa is squared. And centa is 10 to the minus 2. So you square it, you get 10 to the minus 4. And so if you move that upstairs, you get 14.1 times 10 to the 4th over 8. And then you're just left with newtons per meter squared, which is a Pascal. And to finish off the mathematics, I've got 14.1 and divide by 8. And it looks like a 1.76 times 10 to the 4 pascals. Couldn't hurt to think of this as 10 times 10 to the 3rd. So that becomes a kilopascals. And then 10 times 1.7 becomes 17, and so I guess a good way to finish maybe is to say it would be 17.6 kilopascals. All right, so not a real hard one, but one that I thought deserved some conceptual working out, since that's what this chapter really kind of is foundational on, the kinetic theory. All right. Well, let's get to one that I guess I'll call more challenging, more interesting, and again, maybe showing you some of the tricks of the trade on how to do these like PV diagrams and these calculations. So I'll start here and read it, and notice it says that a 4-liter, sample of diatomic ideal gas with a specific heat ratio of 1.4. I'm going to stop right there because that's repetitive, and I guess that helps the problem a little bit easier. I mean, better to say it twice than never at all. But remember, gamma is Cp over Cv. And my point to you about Cv is you count the number of degrees of freedom. And if you remember, the diatomic atom looks kind of like a dumbbell, and so it has 5 places that the energy can go. 3 of them are translation and 2 of them are rotational. So the molar specific heat at constant volume would be the 5 for the 5 degrees of freedom and a 1/2 R for each degree of freedom. And then Cp is what is 1 more R greater. So this would be 7/2 R, coming up to be 7 over 5, coming up to be 1 2/5, coming out to be 1.4. So the fact that they said diatomic also told me the ratio. So again, I guess I'm glad they told me the ratio, but I thought I would take it as a teaching moment and say it's unnecessary, and you probably won't get that fortunate all the time for the homework problems or test problems. They'll either say A, it's diatomic, or B, they'll say it has this ratio. All right, so it's confined to a cylinder and it's carried through a closed cycle. Okay, so let me just focus on that word, closed cycle. That means whatever pressure, volume, and temperature it started with, it changed along the way, but it eventually ends up at the same state. That is the same pressure, the same volume, the same temperature. So I'll take this for a moment to say you should do a PV diagram. And I'm looking at the question here. I'll bring it back into the screen. But it even says, A, draw the PV diagram for this cycle. And that's good, and I will. However, I don't even think that should be a question. That's kind of repetitive. I'm just going to say, always draw the PV diagram. They give us a lot of tools and pictures to work with in our thermal dynamics here. So I'm going to always draw a PV diagram, whether they say to or not. It's just a good tool, kind of like drawing a free body diagram when we did Newton's laws of motion. So, all right, here's my PV diagram. Now, coming back to the reading here, it says the gas is initially at 1 atmosphere. And so maybe I'll put 1 atmosphere right here. I don't think they directly tell me the volume. Oh, yeah, they did, because they said 4 liters. All right, so maybe I'll let liters be on the x-axis. So that was the first part, 4 liters. And the pressure, what I say it was over here, 1 atmosphere. And so they give me the pressure and the volume. So there's where it fits on the PV diagram. I might even put maybe near it 300 K, because they say the gas is initially at 1 atmosphere and 300 K. And first, its pressure is tripled under a constant volume. Then it's expanded adiabatically to its original pressure. And then finally, the gas is compressed isobarically to its original volume. So they give me kind of a 3-step process. The first step is constant volume, isovolumetric. And they said it goes to 3 times, so that's going to be a 3 on the vertical axis. Let me just check that. First, the pressure is tripled under constant volume. Okay, so then it is expanded adiabatically. And that's that little curve we talked about that is not an isotherm. That's if it's constant temperature. It's not a hyperbola. That's if it's constant temperature. This one's a little steeper. And like I said, sometimes just to help me understand, I kind of like to draw the line representing, if it started there and had it been expanded at constant temperature, it would have followed that path. But because it's adiabatic, it does work. So not only does it lose pressure because the density goes down, but it loses pressure because the temperature goes down. And the temperature goes down because it gives off energy as it's doing work during the expansion. Now, the last one, I'll put a little arrowhead for what direction it goes. It says it returns back to its original state. And if we call this like point A where it started, and then point B where it tripled its pressure, and then point C over here where it expanded adiabatically, I don't think we really know this. We don't know how big the volume got. We do know that it says it expands adiabatically until it returns to its original pressure. So that's going to be 1 atmosphere. Okay. And so I guess the diagram would look something like this. And I probably now have completed step A, although There's probably some other things I could calculate, like the temperature at each of these points, the volume at, well, this point, I already have these two. The pressure, I guess I know the pressure, nothing there. Number of moles, perhaps. Anyways, keep that in mind, because as we go to B, it says, determine the volume gas at the end of the adiabatic process. So right there. C, find the temperature of the gas at the start of the adiabatic. And so the temperature up here at B. D, find the temperature at the end of the adiabatic. So we're going to find the temperature at C. D, find the temperature at the end of the cycle. Actually, that's pretty easy. We're back where we started. It's 300. And then E, what is the net work done? And so the two tables I really wanted to show you is I like to make one table involving the states of the points A, B, and C. What is the pressure? What is the volume? And what is the temperature? All right. Now, finding each of those might take a lot of work in itself. So I'm going to leave myself some space. But the other table, and what I was showing you last week, is I like to make a little chart that says A to B, B to C, and C back to A, and talk about what is the change in internal energy as they do each step, what is the work as they do each step, and what is the heat at each step. And then I also like to put a little place for the total, which would be the sum of those. But we also know from the first law that these two have to add up to that one. So, without diving too deeply into the energy part, let's just do the state of the gas. Let's look at its pressure, volume, and temperature, and fill in what we do know. Probably I will use the same units in my chart, although, no, shoot. They're going to ask for energy, so let me switch this pressure to pascals. How about kilopascals? And let's switch the volume to cubic liters, and we'll leave the temperature in Kelvin. And so if you look at A right here, they tell us the pressure, and they give us 1 atmosphere, which we know that to be 101.3 kilopascals. And the volume, they say, is 4 liters, but there's 1,000 liters, so move the decimal 3, and so it's 0.004 for its volume, and its temperature is 300. And those are directly given, other than I got to change units. And so that would be my comment first, is put in what you do know. And then use the different information we have to try to find the unknowns. So that's point A. And I know a little bit about point B, because first of all, it said constant volume. So the volume would be the same at B. And they said it's 3 times the pressure. So this must be 303.9 kilopascals. And in order to get the pressure to go up without changing its volume, we probably need to warm it. And it may not be obvious, but it's got to be 300 times more. I'll show you here. If I take this whole idea of initial pressure times initial volume divided by initial temperature, because that equals to NR. And then from A to B, I am warming it here. But I would now have, in fact, maybe I should put A, that would be better. And so this is the values at A. And then I go to B, so pressure at B, volume at B, divided by temperature at B. That too would have to equal to NR. So the number of molecules doesn't change. And in fact, I actually know the number of molecules, or I can find it. I'll wait to see if I need it. But if you look here, they give you the pressure the volume, the temperature, R. And so we can actually get then the number of molecules. And usually we don't need them in the states. Usually we need them when we start calculating the energy because, it's so much energy per every mole. So we have to know how many moles we have. So I think I'm ultimately going to need that. So I'll just keep in my mind that I could get, based on having these three, the number of moles. But this is where I got that factor of 3, because as I compare the A to the B, noting A to B was isovolumetric, those would cancel off. And so if I go to solve for the pressure at B, and moving the temperature to say, well, it's the temperature at, I guess I want to find the temperature at B. All right. So let me move the temperature at B over to here. And then I'd have the temperature at B, and I bring this over, pressure at A, and then times the temperature of A. And so this is the factor of 3 that was mentioned in the problem, and I said, so this ratio of the pressure, B to A, is 3 times the original temperature, which is 300, and that's where I kind of did this in my head and got the 900 real quick. All right, so now I know the temperature at B, and I think that was one of the questions. I go back and look at it. They asked a lot of questions, but I think I might just answer the pressure, volume, temperature everywhere. And then I know that I've answered their questions. Looking at C, as it said, it expanded adiabatically to C until it got back to that same pressure. So that same pressure is the 101.3 kilopascals. But we don't have the volume and we don't have the temperature. But we do know that B and C are connected adiabatically. And the neat thing about adiabatically was pressure times volume raised to a factor of gamma equaled a constant. So that would mean the pressure at B times the volume at B times gamma, which was given when they said it was diatomic, and they were repetitive. They actually told me it was 1.4, but that was our discussion up here about 1.4. That would be equal to the pressure at C times the volume at C raised to a 1.4. And so now I can put in my units. So the pressure here, and I'll just do it in kilopascals, would be 303.9 kilopascals. The volume at B would be the 0.004. Maybe I should actually comment. You'll notice that I'm setting a beginning to an end, and R is not needed. So it doesn't really matter what units I use. I could have done this in volumes of liters, and then it would match my 4 up here, but it wouldn't match my chart. So I'm going to do it in cubic meters. Likewise, pressure at B could have been done as 3 atmospheres. So there's nothing dictating what units I use up here, but kind of the easy conventional ones is Pascal and cubic meters, since that comes out to be energies of joules. The pressure at C is the 101.3. And then, of course, we are now looking for the volume at C. And so we've got to raise things to a power. So maybe I'll take this to the other side. That's where that factor of 3 comes in. And I'll go 0.004 and 1.4. And volume at C raised to 1.4. Now, I don't know if the math is obvious, but one of the reasons I wanted to do this one, and not really a major one I wanted to show you these two charts and the PV diagram. But when you're solving for this, you have it raised to a non-integer exponent, and probably the thing to do is to raise both sides to a power of 1 over 1.4. That's because, Hang on with that one. That's because when you do that, you make the math a lot easier and get where we really want to go. In other words, when you take volume at C raised to 1.4 and then you raise it to 1 over 1.4, you multiply your exponents, and so you just get volume at C raised to a power of 1, and that's perfect. That's what I'm trying to get. Now on this side of the equation, I would get the 0.004 raised to a power of 1. That's kind of nice. The one that's a little annoying is I would have 3 raised to a power of 1 over 1.4. And if I can show you kind of a fun trick on the calculator, I'm going to take advantage of the reciprocal key. So I'm going to go 3, and I'm going to go raise to a power of 1.4 and reciprocate it. So that is an easy way to enter this math. And I think that can be helpful, just seeing that little mathematical trick there of how you get that. So that right there comes out to be 2.19, and then I can multiply it by the original 0.004, and we are at a little more than 2 times, and it would be 0.008. Why don't I just call it 8? Well, I'll do 3 significant figures. 877. The volume at C. And so if we put it into our little chart here, 0.00877. And keep in mind when you're doing these charts, because PV equals nRT, if you know any of these two, you can get the third. Also, assuming you know the number of moles. Or we can avoid the number of moles by comparing it to any of these other ones. And so maybe I'll do that. Maybe I'll say here the pressure at A times the volume at A over the temperature at A must be the same as the pressure at C times the volume at C over the temperature at C. And so if I kind of move this over, I like to write it as the pressure at C over the pressure at A, volume at C over volume at A, times temperature at A. And of course, you could kind of think about A and C being connected by a constant pressure. That's why there's no effect from the pressure. That ratio would cancel off. They're the same pressure. If we put in 101.3 for A and 101.3 for C, that would cancel off. Or simply put, the reason temperature C is bigger, or put another way, temperature A is lower as we're cooling it down, we got to cool it down in temperature the same way that the volume goes down, and that's what this is saying. So this is 0.00877 over 0.004 for the volumes, and the temperature at A is 300. Grabbing my calculator, I still got that top number in there, so I'll divide it by 0.004. That is that same 2.19, of course, from we got up there, and then times the 300. And that would be then a 600, and I'll call it a 58 Kelvin. And that fits with the idea we've been trying to say in class about being adiabatic. That is, as it expands, it's going to drop in temperature. And so at B, it's 900, and then it expands and cools down to 658, which I say cool down. Those are still both very hot, but that's obviously this is lower than the 900. Temperature is more like an automobile engine. This is the temperature after you burn the gas, and it's hard to imagine that it's cooled down so much when it comes out of the exhaust, because this is high temperature coming out of the exhaust. But that's after it did its work, so that's after it expands, and so the gas is in its cold state, if you will. All right. Well, I've got all of them. Maybe if I go back to the question, I'll be able to kind of say I think I've answered a lot of this. I did the PV diagram. I've determined the volume of gas at the adiabatic. I found the temperature of the gas at the start of the adiabatic. I found the temperature at the end of the cycle. That was an easy one. The only thing I haven't really done is the energy, and it says what is the net work done on the gas for this cycle. And I'm going to just make this problem a little longer because as a demonstration, why don't I fill in every step? Because as I talk about energy, here's the thing I like to get started with. Step one, which ones are zeros? So if you remember going through, we said isovolumetrics first was the easiest one we did, which gives us no work because the volume didn't change. And so we have one of those. From A to B is isovolumetric, so there should be a 0 right there. Another 0 we had was the isotherms. We said the delta E was 0 during an isotherm. Now, for this problem, we don't have an isotherm. Okay, but that's the second 0 I look for. The third 0 was the adiabatic, and we define the adiabatic as Q equals to 0, and that would be the B to C in this one. And in the isobaric, none of the terms were 0. The delta E was not 0, the work was not 0, and the Q was not 0. So 3 of the 4 have a 0 in them, and for our problem, we have 2 of them. We don't have the 0 for this one because we don't have an isotherm. But this is my way of saying, if you need to do these charts, and you will a lot, and you're looking at the energies, I like to make the chart, and I like to put in my zeros. That's the easiest one. Then the second one is I like to put in my delta E's. And the reason I do that one is this is the one that's a state function. This is the one that we said and derived the delta E at constant volume, but we argued that it was a state function, and so it's good for all of these. A to B is a constant volume, so usually that's not a problem, but B to C is adiabatic, but I want to point out that this still works. And then also C to A, which is constant pressure, also works for this. And so I'm going to do and recommend that on step 2, you do this column. Which, of course, you can only do if you know the temperature difference and the number of moles, but we have enough to do that. I haven't calculated the number of moles, but maybe I'll do that now. And getting the temperature difference is going to be really easy now that I already did this chart. So let's get the number of moles, and so I'm just going to go PV equals to nRT, or put another way, the number of moles is PV over RT. And we can pick that anywhere. Why don't we pick it at A? And so this is 101,300 if I do it in pascals. And the volume is 0.004 if I do it in cubic meters. And the reason for that is a pascal and a cubic meter come out to be a joule, which is nice because I'm going to use the 8.31 joules per mole times Kelvin. And then that way this joule will cancel with that joule. These down here will flip. Well, actually, before I flip that one, let me put in the temperature of 300. So the only unit I have to flip is the mole, and that's good. That's what it should come out to be, units of moles. How many moles do I have? So across the top, I have 101,300 and 0.004. Maybe I'll mention it. A little subtlety we sometimes like to do in these is if you already had your pressure in kilopascals, which I do, you could then leave your volume in liters and multiply them and get joules, because remember, a liter is 1,000 times bigger and a kilopascal is 1,000 times smaller. And so instead of going all the way to pascals and cubic meters, sometimes it's nice to leave this in kilopascals, and still you leave that in liters and then multiply them and get joules. But we got enough to learn without playing trickery with the units here. Why don't we just keep going here? So this is the pressure. This is the volume. I will then divide it by the 8.31. I will divide that by 300. And 0. Looks like 163 moles is the answer I was seeking up here. And so if I go delta E, and I'll just do the A to B, I'm going to have the 0.163 moles. I have the CV, and that is based on the number of degrees of freedom. And remember they said it was diatomic, so there's 5 degrees of freedom, so that's 5 times 1/2 R. So that's my CV. And my delta T, I can get back here from A to B, so final minus initial, 900 minus 300. 900 minus 300, so that's 600. And now I have a number here. Okay, so I'll take the number of moles. I will multiply it by the 5/2, that's 2.5, times the R, 8.31. And finally by the 600, and we are looking at about 2026. So up here, I will go 2026. And like I said, I don't know if I had to do that one because they just asked for, what was it again? What is the net work done by the gas? So they're really after this right here. And I'll get to that eventually. But, like I said, I just wanted to do those. Now, with that in mind, why don't I do the other two kind of quickly? The B to the C would be the same calculation, where I'd put in the number of moles, 0.163. I would put in my 2.5 R, and then I'd put in my change in temperature. And in this case, the temperature at C is 658, and at B was 900. So there's my temperature difference. Okay. By the way, notice this is going to be a negative. But we kind of expect that, right? Because it's expanding, and so it's doing work. And you're not giving any heat. So the work and the delta E are the same. So I'm going to be doing work on the environment. The work's going to be negative. Therefore, the delta E needs to be negative. And so this is a negative 819 joules. And if you let me do it one more time for the C to the A, here it is again, 0.163 times 2.5, that's the 5/2, R, 8.31, multiplied by the change in temperature. So temperature A is 300, and the temperature at C is 658. And again, that's going to be a negative number. And again, hopefully that kind of makes a lot of sense. In fact, I could have made this statement that I probably don't need to really calculate that number because I know all three of these have to be 0 because it goes through a full cycle. And so I need to put whatever number makes that come out to be 0. It looks like, other than rounding, I've got it because a 12 and an 8 make a 20, and then that's a 20. But that actually is 11, not a 6. So these two are a 5, too much negative compared to that one, but pretty close. At least to 3, significant figures, it works. So I think there's some rounding there, but other than that, it worked great. And in fact, if it was like on a test, I probably would have never done this calculation using this method. But like I said, I kind of get locked in. And so I'll say it again. and my purpose is taking extra time on this one, is to put zeros for the ones you know, and then do the delta E's, because they're the easy ones. And of course, sometimes you don't have to do the whole thing. And obviously during a test, you wouldn't want to take the time to do everything. But since I'm just making a helpful video, I'll do everything. So then we can talk about the other ones. And since work and Q are both path dependent, I save those towards the end. So before I even do those, I remind myself that these two added together equal that one. So that means as I go through here, if I know any two, I also then can find the third. So that means this must be 2026, because 2026 plus 0 is 2026. And then this right here must be negative 819. Now, sadly, I don't know either of those, so I can't say those two add up to that one. Bummer. There's a lot of things I could do at this place, but the one that comes to my mind is, even though this constant pressure one did not have any of them 0, the work was actually a pretty easy calculation. If you remember, it was minus P times the change in the volume, which came from us integrating PdV. So I'm going to use this equation for work, which is valid only for constant pressure, but that's fine. That's C to A, and I'll get that. And the Q, I won't really need to do anything because now I'll have 2 of the 3, but I could do the Q by going NCP delta T. That would work just fine also. I guess that kind of leaves me in a dilemma of which one should I do. But I'll take this as an opportunity to say, here's some good news on the exam. There's so many different ways of getting there that you only need to find one. But then if you see the other ones, you can cross them to see and check to see if they match. And so usually students can finish this little chart and say, oh, I know it's right or I know it's wrong. Now, just because they know it's wrong doesn't mean they can always find their mistake, but there's so many cross-references that hopefully you can find one of them to get to the right answer, or more than one to cross-check your answer. But I said I would do the work this way, so I will. So I'm going to go minus. Back to my chart. The pressure here is 101,300 pascals. And the volume is the volume at A minus the volume at C. And of course, maybe we should keep an eye on this and realize from C to A, we're compressing it. So we're doing work on the gas. Energy is going into the gas. This should come out to be a positive number, and does it? Yeah, so negative here with a negative there makes a positive number. All right, so this then, I put in my numbers, would be 0.004 minus 0.00877. That's that one. And then times this negative 101,300. And so it comes out to be a positive 483. 483. And so now, if I look here, positive 483, and subtract the 819, I can actually answer the question, and that is the net work. 336. And notice the negative. The negative is a good sign, of course, depending on what you want to do. But I'm going to call the negative a good sign because what that means is I have then put heat energy in during this cycle and got out of it work. This is what we want to do for building an engine. And that's the conversation of the next and the last chapter we're going to do in our introductory to thermodynamics is, what are we trying to do with this heat? Why are we studying this thermodynamics? And what we'd like to do is burn some gasoline and make it do something useful, like turn a turbine or make our car move. Okay? And so we want the Q to be positive and the work to be negative, which this should be 336 positive. And I guess I can attest it here because remember, these two added together is supposed to equal that one. So that's already a negative 12, 12. And when I bring this to the other side, 483, this right here is a negative 1,695. Now again, negative is a good sign because it's taking heat out as we are dropping the volume without changing the pressure. And then as kind of a check then, this 2,026 minus the 1,695 should be my 336 or 331. So I'm off by that, probably that same 5 in there. All right. So I did way more than the question asked, but like I said, I think it really shows a lot of what I want you to see. And so what is the net work? I guess I've answered that right here. 336, negative 336. And I suppose we should look how it phrased it. What is the net work done on the gas? So on the gas would be a negative. What it did on the environment was a positive 336. All right, so like I said, and that took me a long time, but I hopefully think that it was worth it. And so if any of you hung around long enough to witness all those steps, I think you're better off. And you'll see that on the other example I'm going to do here. How about number 39? And 39 says, here is our energy function. And they give it as 3.5. So that would be, let's see, 7 over 2. And this describes the internal energy of an ideal gas. Now that's an interesting number because that means we have 7 degrees of freedom. So I'm going to write it as 7 over 2 nRT. Now maybe I should convince you that that is the same as 7 1/2 kBT. Because remember, Boltzmann's constant is this R over Avogadro's number. Oh, maybe I should say that's per molecule, so times N. And so there's my Boltzmann constant, there's the T over N. But N is the number, and when I divide it by Avogadro's number, that's the number of moles, that's an R, and that's a T. So if you want to write it as nRT, fine. Or if you want to write it as KB or NKBT, usually written NKBT, feel free either way. But this equation is telling me the number of degrees of freedom, and it's telling me a lot of information, and I'm not sure, how much that I need to really know about the number of degrees of freedom. I haven't read the question. Let me bring it back into the screen. And say, okay, so here's my energy function. Describes the internal energy of a gas. We've got 2 moles of a sample gas that always starts at a 100 kilopascals and at a temperature of 300. Oh yeah, I remember now why I picked this one. I like this one because they're going to say, starting with the same initial conditions, let's do this. For each of the following processes, determine the final pressure, volume, and temperature, and the change in internal energy of the gas, the energy added to the gas by heat, and the work done when, and then A, the gas is heated at constant pressure, B, the gas is heated at constant volume, good. The gas is compressed at constant temperature. And then D, the gas is compressed adiabatically. So they make us do all four processes, and I thought that would be a good educational one. And so let's start with A. So A would look like this. Keep in mind, they did say that we have a 2 mole sample, so we've got n equal to 2 there, lowercase n. And we are going to start our gas, and I'll put it on my PV diagram. And let me take a moment to say in the last one, I would always do yourself a PV diagram. It really helps. And in this case, the pressure is going to be 100 kilopascals for starting. They don't say the volume, I believe. They do say it is at a temperature of 300. Of course, using P, V, and nRT, there's T, there's N, I can get V. And so I have a feeling I'm going to need it. So maybe I should find that. But as I read A, real careful, it says the gas is heated at constant pressure. So constant pressure is a horizontal line, and it's now going to become 400 K. And I believe they asked quite a few questions here. They say determine the pressure, the final volume. And so I'm going to have a little chart that says what is its pressure, what is its volume, what is its temperature, what is its change in internal energy, what is its work, and what is its Q. And so these are the two charts I was saying that I like to do during a cycle process. I like to make one chart that's the state of them, the pressure, volume, and temperature, and another little chart that is the change in energies. Now, in this case, I'll just make one giant chart that has all 6 of them, where this is representing the final pressure, the final volume, and the final temperature. And some of these are pretty easy. For example, the final temperature is 400 because they're saying you're going to warm it to that. They also say the pressure is constant, and they give you the initial one, so that's also pretty easy. Okay. What they haven't given me is the final volume, but here's where I'm going to take advantage of PV equals to nRT. And I'm just going to apply this to the final condition and say, okay, the final pressure is and I'll write it as 100,000. The volume and just checking, okay. The final volume is, I don't know. I'd like to know that. The number of moles is 2, R is 8.31, and the final temperature is 400. So looking at the volume, I would have a 2 times an 8.31 times a 400. And then if I divide that by 1,000, I get a volume of 0.0665, and of course I did everything in joules and pascals, and so I'm going to get cubic meters here. I suppose I could move the decimal 3 and get 66.5 liters, but I'm happy with 0.0665 cubic meters for the final volume. And so that's, I think, as much as I really have to do. I have a feeling that later on I'm going to need volume. So why don't I just take a moment and do the initial volume, and you can kind of see then it's going to be 3/4 of that, because I could do something along these lines. The initial pressure times the initial volume divided by the number of atoms divided by the initial temperature is then equal to the final pressure times the final volume divided by the number of molecules and the final temperature. And for this problem, the number of molecules don't change, as well as the constant pressure comes in. And so the initial volume would be then initial temperature over final, and then the final volume. And that right there is the 300 over the 400. And so that's why I said 3/4 of this 0.0665. And that's still in my calculator, so let me go times 3/4 and get a volume of 0.0499. 0.0499. All right, and let me put a double line there, because like I said, to me, I kind of like to do all these calculations with the state functions and then all these with the energy. And let me say the same thing I said in the last one. What I like to do is look for the things that are zero. Now, if you're doing a bunch of them, that makes sense. In this case, it's constant pressure. None of these are zero with constant pressure. So, all right, I'll move on to option 2. Option 2 is the state function. And so that is the delta E. Maybe I'll do something like this so I can still see the delta E here. But the delta E is NCV delta T. And this is where the number of degrees of freedom comes into play. Or back to here, we know there's the N. There's the delta T. And so the 7/2 R must be the CV. And that was our discussion about 7 degrees of freedom. So I could do something like this. Let's see, we know we have 2 moles. And then this is 7/2 R, and R is 8.31. Okay. And delta T is the final minus the initial, which is 100. Maybe I'll save myself a little calculator step and cross off the 2 and call that a 100. So I have 100 times 8.31 times 7. And so this would be 5,817 joules. And then for work, as we mentioned actually in the last one, I can either do NCPDT for Q, or for work, I can go minus P delta V, or I could do both, but those two have to add up to that one. And so maybe I'll just do the work here. So the gas is getting bigger, and because the gas get bigger, this better come out to be a negative number. And so let me go negative times the pressure, which at constant pressure, we know it's 1,000. And the change in volume, final, is 0.0665, and initial is 0.0499. And so, sure enough, it's a negative number, and it's 1,660 joules. And again, these two, work and heat, have to add up to the 5,817. So if I move that to the other side, that is, I subtract the last answer, so the 2 negatives make a positive, and it gets a little bigger, and so 7,400 177. So we had to add that much heat, which, of course, when we added all that heat, some of it went away as work, and so the gas increased by only that much. That's what's left over. This was my example of you have to pour this much water into a bucket that leaks out that much to get a net gain of that much. So you got to pour in a lot more than you get as a net because you lost some out of the bottom of the bucket. It's leaking. All right. Okay. Oh, wow. I've been talking quite a while here, and that's only A. So let's move on to B. Let me again put the PV diagram up here. Let me start it at the same starting spot. And so this is a volume of 0.0499 in terms of the volume, and a pressure of 100,000 pascals, and of course a temperature of 300. And in B, it says the gas is heated at constant volume, and so that is a vertical shot. The pressure goes up until we get to 400. And if I kind of make this chart again, final pressure, final volume, final temperature, and then change in internal energy, work, and heat. Let me start with these three. Clearly, the final temperature is the easy one. That's 400. They tell us they will get it to 400. Okay. And since they tell you it's constant volume, you know the volume's also the same amount, which gives me the option to get final pressure by taking N, R, and final temperature and divide it by final volume. And so I'm going to fill that one in. Okay, so I would jump over here and say, and by the way, it went up by, 1/3. So hopefully this pressure goes up by 1/3. So about 133. So let's see, 2 times R times a temperature of, 400. And then divide it by the final volume, which is also the initial volume, 0.0499. And we are looking at what I would have guessed, 133,000. I'll just call it 200. Why not? So 133,200. And so again, that's how I would work with the states, the pressure, the volume, and the temperature, the state functions. But, or the equation of state. This is also a state function. These are not. And so then I'm going to come over to here. And again, as I always say when I'm dealing with the energies, which ones are zero? Because the only one that doesn't have one of these zeros is the isobaric. And this is isovolumetric, which means it doesn't do any work. And of course, these two add to this one. And so I'm going to go right here and go NCV delta T. In fact, I'm going to go one better. I'm not even going to bother to get out my calculator, because isn't that what I did in A when I was calculating, right? Well, oh, was it up here that I did it? Yeah, up here. And so when I did that up here, even though it's at constant pressure, it was still going from 400 to 300. And so it's going to end up being the same energy here. And like I said, delta E being a state function means I can use the CV, even if it's not constant volume. Although for B, this is constant volume, so that's not confusing. But I used it back here when I had constant pressure. And then, of course, these two have to add up to that one, so that's just 5,817 there also. So that's the neat thing about B. Let me move on to C. C, I think, was the adiabatic one. Let's see. C. C. The gas is compressed, at constant temperature to a pressure of 120 kilopascals. So let me again emphasize. You should always kind of give yourself a PV diagram to help with your thinking. And getting this original one, that's, I guess, not the original. Here's A, the original one back here. I'm going to start it here at a volume of 0.0499 in terms of cubic meters and a pressure of 100,000 pascals. And we are going to compress it. So we're going to go to smaller volumes. And we're going to compress it, as it says, until we get to a new pressure of 120 kilopascals. And so this is the shape of a hyperbola. This is the isotherm. And then if we then put, what is the final pressure, what is the final volume, what is the final temperature, and then we put a delta E, a W, and a Q, we can start filling this in. I didn't show it here, but I should have put, it starts at 300. And that makes that one easy because they say we are compressing it at constant temperature. So the final temperature is still going to be 300. Also makes the final pressure real easy because that's given. They tell you compress it until the pressure gets to 1020. And the only unknown here is the volume. So I can use our ideal gas law to calculate the volume. So grabbing my calculator, I'm going to take the N, which is 2, the R, which is 8.31, the temperature, which is 300, and divide it by a pressure of 120,000. 1, 2, 3. Hit enter. And so it looks like we get a small reduction, and it should, right? It should be a smaller number over here, and 0.0416. And so we went from 0.0499 to 0.0416. Okay. And I'm going to make the same argument over here that you should do the easy one. The easy one are the zeros. And the isotherm has a zero. The isotherm means its temperature doesn't change. Temperature is related to its kinetic energy. That is the internal energy. And so for the isotherm, there is no change in energy. And so since we're compressing it, and we're going to do positive work, heat must also come out. These got to be equal to each other, but opposite in sign, so they add up to 0. So again, I just need to do one of these. And if you remember, we did one of them. We did the work by saying work is the integral of minus P dV. And then we argued that P changes, so you can't pull it in front of the integral, but you can replace mathematically P for nRT over V. And that is an advantage for this case because T is a constant in this isotherm. And so the equation we had for work then was the natural log of final volume over initial, if we go from an integral of initial volume to final. And as I said, we want this to come out to be positive because we're squishing it, and that's perfect then, because when I squish it, this ratio is less than 1, the natural log of less than 1 is negative, and with that negative, gives me positive work. And then once I know that one, I know that one. So I'm going to go ahead and put in my numbers. So minus 2, 8.31, temperature is 300, natural log of 0.0416 over 0.0499. grabbing my calculator. I'll go -2 times 8.31 times 300 times natural log 0.0416 over 0.0499. And hopefully those two negatives now make a positive, and we're looking at about 907 joules. And so 907 joules, which means the heat would be negative 907 joules. All right. So like I said, I like this one. Again, although it's kind of long, it's very useful from an educational perspective because we did or will do all 4 cases. So we've done 3 of them. We did the constant pressure first, then the constant volume, now the constant temperature, and finally the more challenging one mathematically wise, but more interesting one in terms of science and engineering, and the one that's pretty easy to do is the adiabatic. And so coming back to the last question, D, the gas is expanded adiabatically. So again, starting with our initial condition, so this is the 0.0499. This is the 100,000 pascals. This is a temperature of 300. Here's the pressure on the vertical axis, volume here. And we are going to compress it until we get to 120 kilopascals. Now, if you remember, C, where'd C go? In the PV diagram, we were also compressing it along an isotherm. But, like I said, it's sometimes nice to draw isotherms so you can kind of compare. And so this isotherm would have went here. Well, that's what this drawing is saying. The adiabatic's a little steeper. So when we get to this pressure of 120, we are going to be at a little bigger volume. And you might say conceptually that's important is because if we were to compress it all the way down to the same volume that we did for constant temperature, and because we're doing work on it, its temperature would go up, we would actually end up with more pressure than this one. In fact, this curve would keep going up, and eventually it would get to that same volume, but it's going to do it at a much higher pressure because when you shortened the volume and you squeezed it, you also warmed up its temperature. So its ending pressure in the adiabatic is going to be higher than the isotherm if you compressed it back to the same volume. So what we're going to do is not go to the same volume. We're going to go to the same pressure. So by the time we cross this horizontal line of 120 kilopascals, we would have a bigger volume than the, I guess I didn't put it on here, but it should be right here, 0.0416. All right, but same idea. There is a final pressure, a final volume, and a final temperature. And then there is a delta E, and then a W, and then a Q. All right, so on this one, we know its final pressure. We do not know its volume or its final temperature. But the adiabatic process is PV equals, PV to the gamma equals constant. And if you recall, let me just read the problem again here. 39. At the beginning, we concluded there were 7 degrees of freedom, or the CV would be 7/2 R, which means the CP is 9/2 R. And so that means my gamma, which is Cp over Cv, would then be 9 halves R over 7 half R. And so this is a 9 over a 7, which I guess is 1 2/7, and 7's a prime number. 14, so it's what, be 28, 57, 14, repeating. 2 divided by 7. Yeah, 28, 14, and then repeating. Okay, so this is my gamma factor, and I will just call it 1.29 for simplicity. And so what I could do is say, well, if I took the initial pressure and the initial volume and raised it to a power of gamma, that would give me the constant for this gas. And that gas would depend upon the temperature and the number of molecules and, you know, all that. And we could actually find it, but I'll just take a little shortcut. And instead of finding it, just realize it's got to be equal to the final pressure times the final volume raised to a factor of gamma. And so I can take my starting conditions, which is my 100,000 pascals here, and my starting volume of 0.0499, and raise it to 1.29. And that's going to have to equal my final pressure, 120,000. And there's what I'm looking for, final volume raised to a power of 1.29. And if you watched the earlier one, I tried to say probably the best way to do this mathematically is to raise both sides to a reciprocal of 1.29. It's certainly not the only way, but it's the way I like to do it. Because on this right-hand side of the equation here, this put into here, actually, you know what? I don't have so many. Why don't I move this to the other side and call it one factor first? Okay. Because then when I raise it to this reciprocal power, I get just what I'm looking for, final volume. That's the nice thing here. And what's also nice is then this side just becomes 0.0499 raised to a power of 1. It's this one that is a little bit of the pain. In this case, it would be 100,000 divided by 120,000, and then raised to 1 over 1.29. And let me show you again, like I did on the last problem, how I like to do this on the calculator. I like to then, well, I'll do this ratio first, which I'll just do 100 divided by 120. Okay, so there's that ratio, and then I'll raise it to a power, so I'll do the caret, and then I'll just do the 1.29 and then hit the reciprocal key and hit enter. And so that's all this stuff out in front, 0.868, and then multiply it by 0.0499. And we are looking at a volume of 0.0433. And as I said earlier, I would expect this to be a smaller volume than what we started because we're compressing it, but end up bigger than what we got in C, which was 0.0416. And so sure enough, we got something a little bit bigger than that. So in this little chart, I can put 0.0433. Now, as for the temperature, there's a lot of ways to go there now, but I always find it easy to try to remember. If I have any two of these, I can get the third, as long as I also have the number of moles, which, remember, we've been working with 2 moles. That was given right at the beginning. So maybe the best way to get final temperature here for the adiabatic is to say it would be PV over NR, where I'm thinking of the final pressure and then the final volume over the N and the R, so that I'd get final temperature. So the final pressure, we were told we compressed it until we got to 120,000. That's easy. The volume was this one here that we just got here, so I'll just put answer there. We can then divide by the number of moles, 2, and then we can divide by the 8.31. And it looks like we're looking at about 312 Kelvin. And again, well, it rounds to 3. Let's go 313. 313 Kelvin. And that makes a whole lot of sense in this adiabatic because we're compressing it and we're doing work on it, so its temperature should go up. So nice. Now, let's do all these energy ones. And again, I like to say, find the ones that are 0. And the adiabatic, the Q is 0. After that, the next easier one is the state function because that's just NCV delta T. And for this particular problem, that's directly given. There it is. And so I'm going to put in the 2. I'm going to put in the 7/2. 3 point times R. And then the delta T final is 313. Initials 300, so that's a change of 13. So that number here would be 756, which would mean that this number here also has to be 756 because these two added together, according to the first law of thermodynamics, that is conservation of energy, they got to add up to that one. All right. Well, again, you can see that was a good one, and it was also a long one. I know I had on my list number 53 and 62, and I might still attack those, but since this is getting pretty long, and I question if anybody still hanging out, or maybe you took a break and then saw the rest of this. This would be more than past time to probably call it quits to this video. And these, what I think are really good examples. And so if you go back and look at the 5 I did earlier for the other chapter, and then so far these 3 and maybe 2 more, you should be in a great position to be able to do some of these complex ones for the homework and then ace the test. All right, take care.